Good morning, friends. Welcome to Fluid Mechanics classes. I am Assistant Professor Sushant Kumar, Department of Mechanical Engineering, Angadi Institute of Technology and Management, Belagavi. Today we are going to discuss on examples on dimensional analysis. In the previous class, we discussed about Buckingham pi theorem, how to get the non-dimensional parameters, and we also discussed example on Buckingham pi theorem. So we will continue with the examples in today's class. Before going to the examples, we would like to revise a few things. So first one is you have to remember the dimensions for all these quantities, physical quantities. It is very important. Whenever you are solving any problem on dimensional analysis, you need to remember dimensions of physical quantity. So in the examination you won't be having time to derive and obtain the dimensions, so you better practice and remember. As you practice more number of problems, you can easily recall. It just needs practice. This table gives you the procedure for solving any problem using the Buckingham pi theorem. So totally I have listed 6 steps. So already we have discussed this in the last class. I would just like to revise it before going to the problems. So first one, we need to list total number of terms, dependent term as well as independent term. So in a given problem, so total number of terms including dependent and independent variables, so that is equal to n. Once we identify total number of terms, the next step is we need to write the dimensions for each and every term. That is very important. And when you write the dimension, you should cross check twice whether whatever dimensions you have written it is right or wrong. You do cross check, because even if you make slight mistake, though you know the concept, the whole problem would be wrong since the beginning. Next step, once you identify total number of variables, then you write dimensions for all the variables. Next you need to identify the pi terms. How many pi terms we are going to get? So for that we need to identify number of primary dimensions, so that we call it as m. So if you just check the dimensions of all the n variables, so if it includes m, dimension of mass, dimension of length and dimension of time, then our m is equal to 2. Okay, sorry, m is equal to 3. Okay, so in most of the cases m is equal to 3, except in few cases. Okay, so even that type of problems we are going to discuss. So total number of pi terms is equal to n minus m. So what n refers here? N is equal to total number of variables minus m is equal to number of primary dimensions that we have considered. In most of the cases m is equal to 3. Okay, so our pi terms will be n minus m. So once you identify number of pi terms, next and very important step is choosing repeating parameters. So to choose the repeating parameters, so there are again procedures which is available in the next table. Okay, once we choose the repeating parameters, so we are going to write the pi terms and equate the powers of the dimensions and get the appropriate results. So guidelines for choosing repeating parameters. So very important in solving the problems in non-dimensional analysis. If you are going by Buckingham pi theorem, choosing the repeating parameters, very important. So it comes by practice. Okay, as and when you practice more number of problems, you would easily get this. So there are rules to choose repeating parameters. We'll just go through. So first rule is never pick the dependent variable. Okay, never choose dependent variable as the repeating parameter. That is the first rule you have to keep in mind. Next one, the repeating variable selected should not form a dimensionless group. Otherwise, it would be impossible to generate the rest of the pipes. So whatever repeating parameter you are considering, it should not form dimensionless group on its own. Okay, so whatever repeating parameter you consider, it should have some dimension. Okay, so that's what is given in even in rule number 4. Never pick the parameters that are already dimensionless. These are pies already all by themselves. Okay, next one, never pick two parameters with the same dimensions or with dimensions that differ only by only an exponent. Okay, so we should not choose for example, there's a dimension diameter and length. We cannot choose both diameter and length as a repeating parameter. So out of these two we can choose only one, because both have the same dimension. Diameter has the same dimension L, and even the length has the same dimension L. So when such kind of parameters are there, out of two we have to choose only one. So whenever you choose repeating parameters, you choose simple ones which we can easily remember, dimensions easily we can remember. And very important is the guideline number 9. The repeating variables should be chosen in such a way that one variable contains geometric property, other variable contains flow property, and the third variable contains fluid property. Okay, so we need to choose 3 repeating variables. If m is equal to 3, then we need to choose 3 repeating variables. If m is equal to 2, then we need to choose 2 repeating variables. Okay, so how to choose? Okay, so we need to choose one repeating variable which should be from geometric properties like length, diameter, height, and the second repeating variable should be from flow properties like velocity, acceleration, and the third parameter should be from fluid property like viscosity, density. Okay, so you get this as you practice. The efficiency of a fan depends on density rho, dynamic viscosity mu, angular velocity omega, diameter d, and discharge q. Express efficiency in terms of dimensionless parameters. So in this problem, he says efficiency depends on all these 5 parameters. So here efficiency is dependent variable and all these parameters are independent variable. So total number of terms involved in this problem are sum of dependent variable plus independent variable, that is 1, 2, 3, 4, 5, 6. So total number of variables are n is equal to 6. Sum of dependent variable as well as independent variable. So next step is writing the dimension for all these 6 variables. So dimension of efficiency doesn't have any unit, so no dimensions. So I can write it as m to the power 0, L to the power 0, T to the power 0. You know that anything to the power 0 is equal to 1. Next, dimension of density. Density is mass by volume. So dimension of mass is m and dimension of volume is length. Okay, m1 L to the power minus 3 T to the power 0. Next one, dynamic viscosity. Dynamic viscosity unit is Pascal second, or you can also call it a Newton second per meter square. Okay, so once you simplify you get the dimension as m to the power 1, l to the power minus 1, t to the power minus 1. Okay, so next one is angular velocity, radians per second. Now we need for the radians and per second, and the dimension of second is t, and next diameter m to the power 0, l to the power 1, t to the power 0, and the last one is discharge cube. Unit of discharge is meter cube per second. Meter cube dimension is l, l cube per second, t to the power 1. So you need to remember the dimensions of almost all the variables. Okay, there are two important steps in solving the problem. One is writing the exact dimension for the variable, and second one is choosing the repeating variables. So if you are correct in these two steps, your Buckingham pi theorem problem will be right. Okay, so you have to practice and remember all these dimensions for the variables. So next one, if you look at the dimensions, it includes all the three dimensions: mass, length and time. So number of fundamental dimensions, I can take m is equal to 3. Okay, so now you know n, we know m. So number of pi terms are n minus m, that is 6 minus 3 is equal to 3. So I have 3 pi terms: pi 1, pi 2, pi 3. Number of pi terms. Next and very important step is getting the repeating variables. Okay, repeating variables, very important. So we have to remember the rules. Okay, so what the rule number 1 says? It says that never choose dependent variable as the repeating variable. So in this problem, efficiency is dependent variable, so I cannot choose this efficiency as repeating variable. So now I can choose 3 repeating variables from these 5 variables. I have to choose 3. And how to choose that? So one should be from geometry property, and one should be from flow properties, and one variable should be from fluid properties. Okay, we have to choose 3 variables among these 5 such a way that it should satisfy all the conditions. Okay, so let's take up geometry properties. Among these 5, which comes under the geometry properties? Diameter d. Okay, so I have chosen one variable d. Okay, now I need to choose 2 more. Next, let's go to the flow properties. So flow properties like velocity, acceleration, discharge, all this comes under flow properties, and even the angular velocity also comes. Okay, so here I have flow properties as angular velocity and discharge. You can choose either angular discharge omega or discharge. Okay, you can choose any one of these two. I have chosen discharge q. And next one is fluid properties. So here I have 2 fluid properties. So one is the density and second one is the dynamic viscosity. So among these two you can choose any one. So I have taken fluid properties. Okay, so now I have chosen 3 repeating variables. So once you choose 3 repeating variables, let us write the equations. Pi terms. So I have 3 pi terms: pi 1, pi 2. This is pi 3, it's not pi 1. You kindly make the correction. This is pi 3. So we have to write the equation for pi 1. Pi 1 is 3 repeating variables: d, q, rho. D to the power a1, q to the power p1, rho to the power c1. And now we have chosen 3 repeating variables, so we have 3 variables left. So all those 3 variables we are writing in one equation. Always a pi 1 term should be dependent pi term, means we have to always write here dependent variable. Pi 1 should be always dependent pi term. So efficiency is dependent variable, so I should include efficiency term in pi 1. Okay, this is one equation. Similarly, pi 2, d, q, rho, repeating variables with power a2, b2, c2, and dynamic viscosity mu, and make this correction. It's pi 3, d, q, rho, that is d to the power a3, q to the power b3, rho to the power c3, and omega, that is angular velocity. Okay, so now we are going to write the dimension for D, dimension for Q, dimension for rho, that is density, and dimension for efficiency. And pi term on the LHS, it doesn't have any dimension, so we write m to the power 0, l to the power 0, t to the power 0. So now what we are going to do, we are going to compare the powers of all. We are going to compare the power of m, power of l, power of t, so that we get a1, b1, c1. Okay, we'll see it in the next slide. Let's consider first pi term. On the LHS, I have pi term, so which is dimensionless. So we have written m to the power 0, l to the power 0, t to the power 0, m to the power 0, l to the power 0, t to the power 0. And on the RHS, I have all these variables. So let us write the dimension of D, that is m naught l1 t to the power 0 whole to the power a1. Next dimension of Q is written here and whole to the power b1. Next dimension of density is written here whole to the power c1, and dimension of efficiency. Okay, so now we have written the dimensions of all. Let us compare the powers. Now let us compare the power of m dimension. So on the LHS it is 0, and here a1 to the, here m to the power 0, so anything multiplied to 0 is 0. Next plus m to the power 0 into b1, so it is also 0. Next here I have m to the power 1 b1, so it is, so plus c1, and here I have nothing, plus 0. So when I simplify this, I get c1 is equal to 0. I got one constant. I have identified c1. Now I need to identify a1 and b1. Okay, now let us compare the powers of L. On the LHS, there is no power, it is 0, equal to, let's come to the RHS. So here I have L1 into a1, so a1, plus here I have L3, l to the power 3 into b1, so it is 3b1, and here I have l to the power minus 3 into c1, it is minus 3c1, and it is l to the power 0. Okay, so what I get, the equation a1 plus 3b1 minus 3c1 plus 0. When you simplify, a1 is equal to minus 3b1, because c1 is equal to 0, only the remaining terms are a1 plus 3b1, so a1 is equal to minus 3b1. Now let us compare the powers of dimension t. On the LHS we have t to the power 0, I kept it 0. Here on the RHS, here it is 0, so 0. Here it is minus 1 into b1, it is minus b1, and here t to the power 0, so it is 0, and here also 0. So when I simplify, I get b1 is equal to 0. So substitute this b1 is equal to 0 in this equation, so a1 is equal to 0. So I have found a1, b1 and c1. So let us substitute this constant in pi 1 equation. Okay, so once I substitute in this, I get pi 1 is equal to d to the power 0, q to the power 0, rho to the power 0, efficiency. Okay, so anything to the power 0 is 1, so pi 1 term is efficiency. Okay, so I will just solve it for understanding purpose. Otherwise you should keep one thing in mind. Okay, already this rule is discussed. All the dimensionless variables are pi terms themselves. It is one of the rules. Okay, so look here, I just wanted to prove that, that's why I took up this. Otherwise I would have written one per term as efficiency directly. Okay, so after simplifying, I got pi 1 is equal to efficiency. Otherwise we need not have to follow the steps. Directly I can write pi 1 is equal to efficiency, because it is a dimensionless term. Okay, so in the examination, if there is any dimensionless term, it becomes a pi term on its own. Okay, let's go to the next one, pi 2. In a similar way, let us write the expression for, let us find the expression for pi2 term. Okay, so pi2 is equal to d to the power a2 q to the power b2 rho to the power c2 into dynamic viscosity mu. It should be pi2, and we have written the dimensions of all this. Once you write the dimensions of all this, we need to find a2, b2 and c2. These are the constants. We need to find the values of a2, b2, c2. So for that we need to compare the power of m in LHS and RHS. So once you compare the power of m in this equation, okay, you can just check. So c2 plus 1, okay, so c2 is equal to minus 1. I got constant c2, that is equal to minus 1. Next you compare the power of L. Okay, once you compare the power of L, so we get 0 is equal to a2 plus 3b2 minus 3c2 minus 1. Okay, you just compare the power of L here. Okay, so finally we get this equation a2 plus 3b2 minus 4. Okay, now there are two unknowns here, a2 and b2. Let's go for the third one. Compare the power of dimension t. So once you simplify, we get b2 is equal to minus 1. Okay, here I have bt is equal to minus 1. Substitute this b2 is equal to minus 1 here. So then a2 will be equal to 7. So now I know a2, I know b2, I know c2. Okay, substitute these constants in this equation. That is pi2 is equal to d to the power a2. What is a2? a2 is 7, and q to the power b2. What is b2? b2 is minus 1, and rho to the power c2. c2 is minus 1, and mu. Once you simplify, pi2 term will be equal to d to the power 7 mu by rho q. So I got pi1, I got pi2. Next we need to find pi3. So we have identified pi1 and we have identified pi2. Next we need to identify expression for pi3. Okay, so pi3 is equal to d to the power a3 q to the power b3 rho to the power c3 into angular velocity omega. So where a3, b3 and c3 are constants, we need to identify the value of a3, b3 and c3 and substitute, and we will get the expression for pi3. Okay, so we have written the dimensions of all the variables. So once you write the dimensions, we need to compare the power of m, next power of L, next power of t. So we get constants a3, b3, c3, we substitute. So when you compare power of m, so I get the constant c3 is equal to 0, and when you compare the power of L, okay, I get a3 is equal to minus 3b3. Okay, next when you compare the power of t, I get b3 is equal to minus 1. So here I have b3 is equal to minus 1. Substitute this b3 is equal to minus 1 here, then a3 will be equal to 3. So now I have identified a3 and b3 and c3, all the three. Substitute this constant in the equation pi3. So pi3 is equal to d to the power a3, a3 is 3, and q to the power b3, here b3 is minus 1, and rho to the power c3, c3 is 0. So this whole term becomes 1, and omega. So I can write this in pi3 is equal to d3 omega by q. Since q to the power minus 1, I can write this in denominator. So I got a pi3 term. Identified pi1, pi2, pi3. Okay, so now let us substitute the expressions here. So pi1 is efficiency, pi2 I have substituted, and expression of pi3 I have substituted. Okay, so now efficiency is a dependent variable. So efficiency is function of this. This is the final expression what we get. Okay, efficiency is function of these dimensionless terms. So this is the solution for the problem. Okay, let's go to one more example. Go to one more example. So it is on pressure inside a soap bubble. Already this concept we have studied in the module number 1. Okay, so we will correlate our answers. Okay, let's go to the example. Some children are playing with soap bubbles, and you become curious as to the relationship between soap bubble radius and the pressure inside the soap bubble. You reason that the pressure inside the soap bubble must be greater than atmospheric pressure, and that the shell of soap bubble is under tension, much like the skin of a balloon. You also know that the property surface tension must be important in this problem. Not knowing anything other physics, you decide to approach the problem using the dimensional analysis. Establish a relationship between the pressure difference, soap bubble radius, and surface tension of the soap film. Okay, so in this problem there are three parameters. So the pressure difference delta P inside the soap bubble, it depends on the radius and the surface tension. Okay, so there is one dependent variable and two independent variable. Okay, so let's look at the solution. So delta P is a dependent variable and radius and surface tension are independent variables. So total number of variables are 3, n is equal to 3. Let us write the dimensions of all the three variables. So pressure, its dimension is m1 L to the power minus 1 and T to the power minus 2, and radius, it is m to the power 0 and L to the power 1 and T to the power 0, and surface tension, its dimension is m to the power 1 L to the power 0 and T to the power minus 2. Okay, so we have identified number of variables 3 and we have written the dimensions for all the three variables. Okay, so now all m, l, t all are involved in the dimensions. So let us consider our fundamental dimensions equal to 3. Okay, so now number of pi terms is equal to n minus m, that is 3 minus 3 is equal to 0. Okay, but how can we have 0 pi's? Something is obviously not right. Okay, in that case, when the pi is equal to 0, okay, you check your list of parameters and check your algebra. If everything is right, then you just reduce m by 1. Okay, if everything you have checked everything, there is no mistake, okay, then in that case you reduce your m by 1. Okay, so now I will make m is equal to 2. So n is equal to 3, m is equal to 2, then my number of pi terms will be equal to 1 here. So thus we now have m is equal to 2. Number of pi terms is equal to 3 minus 2 is equal to 1. So thus we expect 1 pi, which is more physically realistic than 0 pi's. Okay, so next step is we have to choose two repeating variables. As m is equal to 2, we have to choose two repeating variables. Okay, so here we have only two variables, that is r and sigma, because they are independent variable. So delta p we cannot choose as repeating variable because it is dependent variable. Okay, so we'll consider radius and surface tension as repeating variables. So pi 1 is equal to r is repeating variable, sigma is repeating variable. So r to the power a1, sigma to the power b1, and delta p. Okay, so let us write the dimensions for this. So pi 1, it doesn't have any dimension, so m to the power 0, L to the power 0, T to the power 0. I have written the dimension of r here to the power a1 and dimension of surface tension to the power b1 and dimension of delta p here. Okay, so now let's compare the powers. Let's compare the power of m. So here LHS 0 and here 0 into a1, it is 0, m to the power 1 into b1, it is b1, plus here I have m to the power 1, so b1 is equal to minus 1. Okay, now let's compare the power of L. L in the LHS, sorry, here LHS is equal to 0 and here it is L to the power 1 into a1, it is a1, plus L to the power 0, it is 0, and here L to the power minus 1, I have minus 1 here. So a1 is equal to 1. Okay, now we have found out constants a1 and b1. Okay, let us substitute this a1 b1 in the equation here in the equation. So pi 1 is equal to r to the power a1 is 1, r to the power 1. Next, sigma s to the power b1, b1 is minus 1, so sigma to the power minus 1 delta p. Okay, so pi 1 is equal to delta p into r divided by sigma s. So this is the pi term that I got. This pi term, whatever I have got, it is more similar to the Weber number. It is more similar to Weber number. Since there is only one pi, which is function of nothing, this possible only if pi is constant. Thus we can write pi equation as pi 1 is equal to delta pr by sigma s is equal to function of nothing. Okay, so it is equal to constant. Okay, so delta p is equal to, so when you cross multiply, delta p is equal to constant into sigma s by r. So this is the relation. Okay, this is the relation that we got using the dimensional analysis. If you go back to module 1, where we studied the pressure inside a soap bubble, we had got a similar expression, delta p is equal to 4 into sigma s by r. Okay, so in this case the constant is equal to 4. Delta p is equal to 4 sigma s by r. Okay, so similarly even you can find the relation, dimensionless relationship, for other examples, okay, that we had discussed in module 1. So these are the examples on dimensional analysis. Go through them. If you find any difficulties, kindly contact me. Thank you.